Hey everybody, Mr. R back with you again, and today, as advertised, we're going to be chatting about aircraft systems. So while I'm babbling over here, pull up Chapter 7 in your Pilot's Handbook of Aeronautical Knowledge, and we're going to be following this chapter pretty close today, so you're not going to see all of the fancy slides that I did before, primarily because we're just going to be following the chapter. In this chapter, you're going to see a lot of the different systems of an aircraft. Remember, in an aircraft, there's a lot more to it than just the wing and a cockpit. There are a lot of systems that make everything go in that airplane, and we're going to be touching on a lot of them here in this particular chapter. Know also the basic element of this, again, that I stress every single one of these lessons, and primarily because normally, we give that section on aircraft engines, we give that an entire day in our regular ground school class. But this is just to give you a little insight as to the number of systems that you may see in an airplane, what they are, and just a little bit about how they work. We do not go in depth in these like we do in the regular ground school. Also, you will notice that our episodes here look a little bit different, so that's part of the evolution of things here as we move along here educationally. So it may have a little different look and feel. We'll see if you pick that up here just a little bit later. So, without further ado, let us begin the festivities here with Chapter 7 and talking about the power plant. As I scroll down through the system here in the power plant, we're going to start here with looking at engines. This first funny-looking engine that you may see right here, this radial engine, is called as such primarily because of the fact that in a radial engine, most of the cylinders, which we haven't talked about yet, are sort of in a circle. That's one type of an engine that you may see. Another one here is something that is what we refer to as a horizontally opposed engine. That horizontally opposed engine means that instead of a circle here with these cylinders, the cylinders are actually opposite each other horizontally, ergo horizontally opposed. I know. They're a little bit offset to allow the inner workings of the engine to kind of work beside each other, but they're pretty much across from one another with regard to being horizontally opposed. And one of the things that makes those horizontally opposed engines attractive is that from actually a performance to weight ratio, they're pretty good, they're easy to work on, relatively straightforward in their design and operation. Here in figure 7.4, you'll see some of the items that we talk about in a little bit more detail in our regular class, and you can take a look at these as you will here in figure 7.4. Here's a two-stroke engine in 7.3. We don't see a lot of those in aircraft, but we do see here the four-stroke engines. In figure 7.5, this is going to be an illustration here of the strokes of a normal four-stroke engine. Now, I do want to tell you that the four-stroke engine is something that the FAA will test you on. Why? Because it's the predominant engine found in most aircraft that are piston-powered aircraft. And they want to make sure that you know how those engines operate. And the reason for that is because the more you know, the safer you are. So, they're going to be testing you on these various strokes. These various strokes are going to be referred to as the intake stroke, compression, power, and exhaust. In the intake stroke, as you can see here at the top, the intake valve opens, air and fuel are entered here into the combustion chamber as the piston pulls down. That pulling down here of the piston creates this void to help that air and fuel enter, and it can enter regardless of whether or not it is a carbureted engine or a fuel-injected engine, which we're going to talk about here in just a little bit. But that's how that fuel and air enter the combustion chamber here on the intake stroke. That is compressed the next time this crankshaft goes around. That piston moves toward here and squeezes the fuel and air to make a more efficient mixture of fuel and air, so that on the next stroke, which is the power stroke, when the spark plugs spark and ignite this fuel-air mixture, this is the part that really supplies the power to that engine. And it forces that piston down, turning that crank, and then it moves around one more time, pushing the piston back up on the exhaust stroke, which then moves the byproducts of combustion out of that cylinder. Byproducts of combustion, they can be a little bit of carbon, a little bit of water in there. Water, strange you ask, take the class. And as well as heat. So those things are then expelled in that fourth stroke, which is that exhaust piece. Those are going to be some test questions that you have on your FAA knowledge exam. We also are going to look at the propeller. We've talked about the propeller before. Here in figure 7.6, you're going to see a little bit segmented view about what a typical propeller might look like. And it's interesting to note on this that you'll see here that the blade angles themselves are a little bit different depending upon how far they are away from the hub or center portion of this propeller. The further out toward the end of this propeller blade that you get, you'll notice that it actually does not have the angle that it has here closer to the hub. Why is that? Well, if a propeller, if you think about what its job is, remember a propeller is basically a spinning wing. It's a spinning airfoil. That's what a propeller is. And as that moves around, there's going to be some torque applied to that propeller. It moves slower at the hub than it does way out here at the tip. So if that had the same type of blade angle for the entire length of that blade, you're putting a tremendous amount of pressure on that blade as you start to get away from that hub, and those things will just fly apart. So the trick is to actually manufacture a blade that puts even pressure along the blade all the way from the hub to the tip. And that way you have a propeller that's going to stay together, which is kind of important, I'm told. So if you look down here a little bit further here at figure 7.7, you'll see exactly what I mean here. So understand that you have a propeller. So that propeller can come in a couple different flavors. One is something that we refer to as a fixed pitch propeller. A fixed pitch propeller has the same twist all the way through the blade from the hub all the way to the tip. It doesn't change. That propeller can be made in a couple different configurations. Let's say that a pilot with a fixed pitch blade wants one for climbing. Let's say that he does a lot of backcountry work and he's flying a tail dragger. You can actually have that blade made so that it emphasizes the climbing element, but it's going to sacrifice the speed in cruise. Conversely, you can have a cruise blade put on an airplane. You don't get the climb performance that you might otherwise, but you're going to get better speed in a cruise configuration. Well, then we have a different type of a propeller system, and that's what we refer to as a variable pitch or constant speed propeller. And what that does gives the pilot the opportunity to actually change the blade angle to help to maximize then the phase of flight that you happen to be in. When you're climbing, you can set your propeller so that it can climb very well, but then you can also make an adjustment when you're ready to cruise to help make the airplane cruise better. So you have a fixed pitch and you have a constant speed or variable pitch propeller. So those are a couple different flavors of propellers that you might see, and those propellers can be at the front end, or in some cases in a pusher, you can actually find those at the back end of airplanes. We're talking about induction systems. Induction systems, that's kind of a fancy way of saying here's how air and fuel kind of get into that cylinder that we talked about before. So carburation is one way, fuel injection is another. As we look here, first of all, they look at carburetor systems. Figure 7.10 gives you a look here at what a carburetor looks like and how it works. We won't be going into the carburetor system in depth, but just know that you have a fuel reservoir here, and then as air gets pulled through this venturi here at the inlet, then this valve you can open, the pilot can open up this valve to make the plane go faster, go slower here, to allow more fuel and air to go into the engine, into the cylinders of the engine, where combustion takes place. We don't see with most modern aircraft as many carbureted systems out there on engines anymore. One of the reasons being is that with more modern aircraft, they use fuel injection, which we'll talk about here in just a second. But the other thing is that carbureted engines, even though we flew them for a long time, they can be a little finicky when it comes to their performance with regard to icing up, because the butterfly valves and that inlet that you see here in this particular configuration, at various different temperatures, even temperatures a lot warmer than you might think, these can actually ice up. They ice up because that air is moving very fast through this inlet and through this little squeezed section here called a venturi. And when that air is sped up, not only do you have here a lower pressure that we kind of talked about here before with regard to the wing, but there's a change in temperature. That temperature actually lowers, and any water vapor that is in the air that's getting pulled through that system can actually freeze. Well, when it freezes, it changes then the way that venturi looks through that system, so that throat actually can compress, as well as that ice can form on that butterfly valve. And I think you can imagine that has an effect on performance. So most systems now use what we call, and this figure 7.11 here shows exactly what I was talking about. Most of the systems now, they will use fuel injection with those. A fuel injection system, as you can see here in figure 7.13, there is a fuel manifold that is normally either at the top or the bottom of these engines. Typically it'll be mounted on the top. And then it will meter the amount of fuel to be sprayed into the cylinder as air is being pulled in from an air inlet into the engine. This is a preferable type of a system. It doesn't have some of the little quirky natures of the carbureted engines here, and there are some drawbacks to this. The nozzles have to be clean, so you really have to watch how you're operating your engine. And it's typically a bit more of a reliable system, more so than the carbureted system. You can see here in this particular illustration what I was referring to here in a top-down view of these horizontally opposed cylinders, but you'll notice they're not exactly straight across. They're offset slightly, again, to kind of allow for the inner workings of that engine to kind of move back and forth. A little bonus information for you there on that illustration. Now, as we move through here, we can look at superchargers and turbochargers. What is a supercharger, turbocharger? Well, before we get into that, why would you need one? Well, if you think about a normally aspirated engine, which is what we've been talking about before, that basically means that the workings of that engine, when those cylinders move in and out, the pistons move in and out of the cylinders, it creates a void, creates a vacuum, and it pulls air in. Well, that air can only get pulled in as much as that engine works, or you have a little bit of that ram air effect in those air inlets sometimes to kind of give you the air. What is it that we need to make combustion? We need fuel, air, and spark. In the air, we need oxygen. So, of that oxygen, that's what we do to create fire. The more air that we can put in those cylinders there, the more oxygen we have, and the more oxygen we have, the more fuel we can actually use to create a higher pressure charge inside that cylinder to create a little bit more of an efficient workload on that engine. So if we had a way to force more air into those cylinders, wouldn't that be great? So with that, we enter the superchargers. The superchargers or turbochargers do just that. What they do is they allow here, as in figure 7.15, what they do is they have a system here where they actually can pull here through a series of turbines here, as well as some of the airflow tubing that they have here that goes into the engine. You can actually pull more air here. It gets compressed. It gets forced into these cylinders, better combustion, and then that gets the exhaust gases get pushed out. The exhaust gases actually are the things that drive that turbine. So you can control this. The pilot can control here the amount that is actually being forced into that engine. But the big difference here is the fact that now, instead of basically with a normally aspirated engine, one that's not turbocharged, typically at 16 or 17,000 feet, you're pretty much about done. That's going to be your service ceiling. Not necessarily that your plane can't fly any higher, it's just that your engine can't pull in enough oxygen in the air at that altitude to be able to keep up with performance. Now, if you can force more of that air in, now that same airplane with that different turbocharger and perhaps a different engine in it can now fly to 26, 27,000 feet. Now you can get up above the weather. You can actually burn less fuel up there depending upon the type of engine that you have. So it allows you more flexibility with that. More flexibility, so you've got some pros here with regard to a turbo or a supercharger. There's also some cons. It's an additional system that goes on your airplane. It is an additional system that you have to monitor and, dare I say, baby. But again, you also have some expense because maintenance on these turbocharged systems and the engines that are actually used with turbocharging systems, they can be pretty expensive. So for instance, the engine in my airplane, if I were to go out and buy a new engine with that, it would actually cost more than my first 2 houses that I bought combined. So yeah, they're kind of pricey, but they are nice. So with that, we'll press on here, look here, and we talk about the high altitude operations. We talk about ignition systems, the ignition systems on the airplane. And this is where we start getting into some of the electronics of the aircraft here. So with this, you have the spark plugs that we talked about there before. You actually have here a diagram here in figure 7.16 that kind of talks about this. We have 2 different magneto systems that govern the electricity, the actual spark, and the timing of that spark, kind of how all of that works here within your cylinders. One of the things that is a little different in an airplane as opposed to a car, in a car you basically have 1 spark plug per cylinder, but in an airplane you're going to have 2. One of the reasons that you have 2 is that you get more efficient burn of your fuel-air mixture, and therefore you get a little more power associated with that. So you get more performance with 2 spark plugs. But the other thing that you get is you get safety. Let's say that if we just had the one system like we do in a car and that system failed, well, now you've gone into stealth mode and you're making an off-field landing or hopefully landing at an airport, if you've managed your energy properly. But with an airplane, if one system goes down, you still have spark being applied to those cylinders with the other system. You get a degradation in performance, but you can still get to an airport to get your system kind of figured out. So that's one of the reasons that we have a dual magneto system in airplanes. We look at oil systems. Oil is one of those things that we talked about in a previous class that we talked about when we were referring to the OODA loop. Well, the oil system here, as you look at the bullet points here, you can see that you have a lubrication element to it because, as you can imagine, when you look at the cylinder and the piston, you have a lot of metal that has the potential to be scraping together. Well, that scraping element, you want to minimize that as best you can. That oil lubricates those connections between all of the metal parts that are working inside that engine to keep it sliding together here, to keep them moving easily without creating the grinding with that. So, as you might expect, you also have to have an oil that has the ability to withstand the temperatures that you're dealing with here with an engine. So that oil system, you have a sump where you can add oil here to keep a certain amount of oil based on the engine that you have. You have a pump that moves that oil around. Not only is the oil there to help lubricate, but it also helps cool the engine because cooling is also important. So those little fins that you had looked at there before on those cylinders, that is one of the cooling mechanisms. But that cooling mechanism only works when that airflow is moving through the engine cowling to help keep that airplane cool. Most aircraft engines are not water-cooled engines like you find on a car. It's a lot of weight, a lot of moving parts that you don't necessarily need if you're handling the energy properly in your airplane. You have another system here whereby air can move inside the cowling of your aircraft, and it actually, through a series of baffles, can be controlled so that air moves in and around those cylinders to help cool them there as well. So we have the exhaust system, starting system. We talked about the exhaust system. The exhaust system also is one of those systems that actually can help apply heat inside your aircraft at high altitudes or seasonally as you need it. When we look here at combustion, you can look here. This is what we call normal combustion. You want to make sure that you do have normal combustion and you don't have anything that we refer to as pre-ignition. Pre-ignition can be kind of a bad thing to kind of have happen in your aircraft. So you want to make sure that you're using the right grade of fuel. We'll talk about fuel systems here in just a second. Here with electrical stuff, you can look here at figure 7-20. This talks about a starting circuit. I know that when people look at this for the first time and they see a lot of these little things that they may not be familiar with, the electrical system is one of the systems that we actually spend 2 days going over in a regular ground school class. It's not that it's necessarily all that complicated. It's just the fact that there are a lot of new terms that you're going to hear in that most kids probably haven't heard before. So this kind of talks about here a little bit electrically about how that works. We're going to get into the electrics here just a little bit more. One of the things that they have out here now is something called FADEC, Full Authority Digital Engine Control. As computers get smarter and smarter and smaller, they can control more of the operations in an aircraft. FADEC, as you can read here, is going to be one of those systems that can do a couple of different things for us. In some systems, it can actually govern that propeller that we talked about there before. It can also govern the amount of fuel-air mixture, so it can take care of your mixture for you. So that in essence, with some FADEC systems, you just have single lever operation. I have mixed feelings about that, only because of the fact that it's great when everything is working. But the simpler a system is that then usually the less susceptible that you are to having something go wrong on a system. 6 of one, half a dozen of the other. Turbine engines here, like you see on a jet engine, we'll look at those here just real quick. With jet engines, with turbine engines, you basically have a system that pulls in a tremendous amount of air, squeezes it, compresses it, then ignites it to then use that for energy. So it sucks a ton of air in at the front, squeezes it, ignites it, blows it out the back. That is generally how these work. Clearly, it's a little more complex than that. So you can have a turbojet engine that works here like the one that you see in figure 7-23, or you can have an engine that actually works similar to that actually spins a prop. That is like a turboprop engine. So you basically have a jet engine that turns a propeller. With this here, you can see turbofans. Turbofan systems, those are a lot of systems like you'll see now in modern jet aircraft there. Again, we're not going to spend a tremendous amount of time, but just to show you kind of how all of this works. With each of these systems here and some of these subcategories, each one of those comes with its own separate gauge. So the thing to think about here is that the more complex that systems get inside an airplane, the more elements there are to monitor by the pilot to make sure that everything is working correctly. So, more complex, more systems, more monitoring, typically more training and more experience for the pilot. Next, we're going to get into some of the airframe systems that they refer to in Chapter 7. One of those has to do with fuel. Remember that you've got to have 3 things for combustion: fuel, air, and spark. In this section, we talk about the fuel itself. We talk about how it actually gets to the engine. Here in figure 7.30, you can look here at a gravity feed system. For instance, if you have, let's say a high-wing aircraft, well, you've got your fuel held above your engine. Well, gravity can be your friend, helping move that fuel down to where it's needed in that engine. Low-wing aircraft that have fuel that are then it's going to be below that engine, you're going to be completely dependent on pumps to move that fuel there. You have engine-driven pumps. You also have electrical pumps. And these pumps, they can be used at various phases of flight. Some of them need to be turned on when you're starting the aircraft. Some aircraft need priming to start the aircraft, where it forces some fuel into the cylinders to get the aircraft started, so that the actual main engine-driven fuel pump can then start pulling that fuel into the engine. So with that, we can look here. There are various fuel selectors that some aircraft have, depending upon the kind of airplane that you have. A lot of high-wing aircraft will have a both option here when it comes to selecting your fuel, where it'll pull out of both the left and the right tanks. Most low-wing aircraft, you will have to decide, do I want to get it pulled from the left or the right? A thing that you also have to consider when you're doing that is the weight and balance of your aircraft, because you don't want to just drain one wing completely and then move on to the other, because that will give you a pretty entertaining imbalance in your flight. So you have to monitor that. There's different kinds of fuel, as you might imagine, although there are not as many as there used to be. Figure 7-23 talks about the various different types of fuels, and back when I started flying airplanes, you did see different types of fuels. Now, everybody is using 100 low lead or Jet A. Jet A is going to be for jet engines or engines that are run by diesel engines. 100 low lead is more akin to gasoline that can be found in your car, a little bit different. It's going to be a higher octane, the 100 octane, and it's also going to have a low lead additive put in there to also kind of help with some of the lubricating properties associated with that type of fuel. So that can all be tubing-wise moved into your engine to use as your engine needs it. There are, as you might imagine, refueling procedures that you need to definitely be aware of. When you refuel an aircraft, the heating systems that I mentioned before, you've got a couple different varieties. One is where you capture some of that exhaust heat coming out of your engine. You have a pipe that is your exhaust pipe, but then you have another kind of a capture basket around that called a manifold. And when that heat that's coming through gets captured in this hollow basket, and then air can actually be pumped through that basket inside the cockpit to warm you. Now you have to be careful to make sure that this basket that surrounds that exhaust tubing doesn't have any holes in it, because you don't want to be blowing carbon monoxide back into the cabin, because physiologically we're just not equipped for that. The other type of a heater that you can find are going to be heaters that you may find in a twin-engine aircraft that don't necessarily have the ability to pull that warm air in off the engine, because your engines are now over here at the side of your cockpit. They have a separate heater that is actually run by the fuel from either the left or the right side of your engine, but it's a separate heater that can supply heat to your cabin. Here on the electrical things, I want to show you a couple of different schematics here. As I mentioned, we spend 2 days going through the electrical system. So if you take a look here at this schematic here on figure 7-34, anybody feel like that? A little cross-eyed? Again, the reason that we spend a couple days on this is because there are things that kind of go on electrically here in an aircraft that most students have not had the experience yet of learning about. A couple of things. You have electricity, as you might imagine. Remember, electrons. So you're going to be bouncing some electrons. The more modern systems, they're going to use more electricity. You've got a couple of different types of systems that you have inside an airplane. You can have either a 12-volt system or a 24-volt system. Those systems are actually 14 and 28-volt systems. When it comes to the alternator that actually supplies the electricity to the battery, that everything runs through that battery to run through your systems, and it's sort of like your reservoir of electrons there. That alternator, what it does is that it's attached by a pulley system to your engine. So as your flywheel of your engine is spinning around, it will also turn that alternator. That alternator creates, through a system of diodes, it creates electrical energy that then is actually in the form of an alternating current into a direct current. So you've heard terms like AC and DC. No, it's not just the most awesome band ever, although they are. It's also a way that electricity gets moved around. In your home, typically, you're going to be supplied through AC, or alternating current. That alternating current means that there are electrons that are going to be in those lines in your home. But unless they get activated, they just kind of sit there. But when they get activated, they sort of move back and forth. They kind of alternate back and forth, and that charge gets passed along from one electron to the next, so that then it can ultimately flow through whatever it is that you're attempting to power, your vacuum cleaner, your television, whatever, so that it can actually turn that device on. So in an alternator in an airplane, it starts out with that alternating current, but then it gets converted into a direct current. A direct current is basically a loop that moves electricity in one particular direction. And then you have a particular item that can be connected to that loop. And once you have that circuit which moves this and closes a particular element that allows whatever device that's connected to that circuit to be on, then it can be activated with that. But you've got to have that alternator working, because if you're just thinking, okay, well, I'm going to charge my battery and off we go, well, you may only get about 30 minutes of use out of that battery before it's dead. And when an aircraft battery goes completely dead, it has to be replaced. And when you start replacing $600 and $800 batteries in an airplane, that gets a little expensive. So that alternator has to be working to keep that battery recharged, to keep sending those electrons around that loop that we discussed, to keep all of your power on. So that's kind of the way the electrical systems work. You have various elements in your aircraft that are attached to these things called buses. So it's basically categorized based on either how you need it, when you need it. It can also be broken apart for essential use. Like, for instance, there's a thing called an essential bus that if the chips are down and your alternator quits working and now you're just down to drawing the electrons out of your battery, then you can prolong the duration that that battery will actually supply you meaningful electrons in your systems by reducing the demand on that system by saying, okay, I don't need 2 radios, 1 is fine. I don't need 2 navigation systems, I can make it with just 1. And it starts putting all of those essential items just on one circuit. So with just the flip of a switch, or perhaps 2, you can then relieve the draw on your electrical system to just the essential items. Again, we spend 2 days going over this in a regular class. So, and with that also in an electric class, we also talk about electrical flow kind of as water. And we think about sort of that water flow analogy to kind of how electricity moves around. It's really pretty cool. And I want to give props to my buddy Rod Machado, who has been a mentor to me for a long time. And I first saw his analogy of water flow with electrics, and I thought, oh, that's brilliant. It helped me understand the systems better. So we move on here with the electrical systems here. Landing gear, that's also a system. You can see here in 7-37 that this is a type of landing gear, tricycle gear, that you can see. This is associated with most training aircrafts, the small Cessnas like this. That's kind of the way that they work it. We also, here again, you'll see something that we refer to as a tail wheel aircraft here, where the main gear is slightly forward and you have a wheel back here at the tail. This is also referred to as a conventional gear aircraft here. You can also have gear that's actually retractable in certain more high-performance aircraft, that they can actually just pull the gear up, make the aircraft a lot more aerodynamic. We have pressurized aircraft here also. Now, what's the difference between pressurized aircraft and non-pressurized aircraft? So, in a pressurized system, you have seals that seal off everything inside the fuselage, and you have a pump that pumps air and oxygen into the cabin of that aircraft to pressurize it at a certain MSL, at a certain sea level rating. Most aircraft are going to be pressurized to feel like you're at about 8,000 feet in most aircraft. In some aircraft that can take higher pressurization, they can get that down to about 5,000 feet, but it allows you to be at high altitudes, to a certain altitude, without having to have an oxygen mask on. Now, if you're in a training aircraft, or if you're in an airplane like mine that even has a turbocharger, you know that you get to a certain point where those oxygen molecules in your atmosphere get pretty few and far between. So you have to rely on supplemental oxygen that you have to wear. That can be through a nasal cannula that you can wear up to a certain altitude, but you get to a certain altitude and that normally doesn't work very well. So at about 17,000 feet, I actually have to put a mask on that gives me a better seal that can actually apply a little bit of pressure here also, not quite like the big pressure masks like they use with fighter pilots, etc. But it's a similar type of a concept, because once you get above 12,500 feet for a period of 30 minutes or more, you have to be on some form of supplemental oxygen in accordance with the regulations. And above 14,000 feet, you have to be on it anyway. And so with that, the reason being is because physiologically, you start running out of oxygen, your brain doesn't work very well. So that's one way to do it, but it limits you with the altitude that you can actually fly based on the type of oxygen system that you have available to you. If your aircraft is pressurized and you can pressurize that cabin with the air and the oxygen already there, then that takes care of your need to actually wear some form of supplemental oxygen. So it's quite a bit more convenient. But it is another system that also requires maintenance and observation by the pilot and the crew. With this, they talk about the pressure here also in figure 7-41, excuse me, and then here in figure 7-40, they talk about the pressure systems here as well. Oxygen systems, oxygen regulators, oxygen masks, how all of those work. This is that cannula that I was telling you about here before. You actually have a little meter that you can dial in, and on this meter you can say, okay, I'm at 12,000 feet. You dial that meter so that the little ball inside the meter is at 12,000 feet, and you should be getting the proper amount of oxygen to keep all of your faculties moving up here. It's also a great idea to keep what we call a pulse oximeter in your aircraft as well. It's that little thing that they slip on your finger. You may have had this done at the doctor's office, where they can actually measure your oxygen saturation rates, because they do it right here, measuring this in the capillary beds of your fingers. And they can tell you, are you getting enough oxygen? So if you're at 12,000 feet, you have a nasal cannula, you've got it dialed in at 12,000, a couple of minutes, you check your O2 levels here, O2, oxygen, there you go. You check your saturation levels here, and if it's not enough, if it's a little bit low, you can actually add a little bit more oxygen to make sure that you're getting enough. Smokers, if people who smoke cigarettes, they are more susceptible to oxygen deprivation because their lungs are just not working the way that people who don't smoke do. So they have to be very careful about the type of oxygen and some of the flight levels that they actually fly in just because of that. So keep that in mind as well. This gives you an idea of the type of a mask here. This is almost exactly like the mask that I have in my airplane here that you wear. The pulse oximeter, this thing that I just talked about here before, it measures your pulse as well as the amount of oxygen saturation level. Anti-ice and de-ice systems. Why in the name of Orville and Wilbur would I need some form of an anti or de-ice system? That just seems like that would not be good for airplanes. Well, sometimes when you're flying an airplane and you're flying through a cloud, which is visible moisture, is that at certain temperatures, certain times of the year, and certain altitudes, that water, the water vapor in those clouds, can actually stick to an airplane. And when it sticks to an airplane, then it causes several problems with that airplane as you get ice accumulations on your wings especially. What that does, it changes the shape of the airfoil of your wing. Now your airplane is not going to fly like it used to because it's not getting the airflow that it needed across that cambered surface at the top of your airplane. The other thing that it does is that it adds weight. Now your airplane is heavier. Think that might also have an issue with your control systems on your airplane? Yep. Because remember, it's not just this wing that's here, usually at the midsection of your airplane, that's going to be collecting ice. You've got this whole empennage mechanism at the back of your airplane that's also getting ice. So now you've got some issues. So does that mean that we have no solution to any of this? Not so fast. Some airplanes, more high-performance airplanes, are going to be equipped with various anti-ice or de-ice systems. The one that you're looking at here in figure 6.48 is going to be a rubberized leading edge that is going to be on the leading edge of this wing. And it's a rubberized system. And the way that works is that the pilot actually has access to a switch. And in that switch, he can say, inflate this system. So those bladders inside that rubber leading edge, they blow up. And when that blows up, it pops that ice that has formed on that leading edge of that airplane, and it sheds it back behind the airplane. That keeps the air flowing the way that it needs to over the wings. Now, the pilot has to kind of be careful about the type of ice and how the accrual rate of that ice on that leading edge, because if the pilot sees that ice out there at the leading edge of that airplane and says, ooh, I need to get that off, well, if it's the wrong kind of ice, that pilot may actually activate that system, those bladders inflate, but the only thing that happens is that it just moves the ice forward slightly, and now you've got this cavity that forms between the rubberized bladder of the leading edge and the actual ice component over here itself. Well, now you're in a bit of a pickle. You can't do much about it because now your de-ice boots, as they are referred to, are not going to work properly because they can't get out there and move that ice. So you kind of have to know what kind of ice it is, the accrual rate, and to know when to activate that switch for this type of system to truly be effective. By the way, it's an additional system that requires maintenance. You have to get out there, and every so often you have to apply this coating on there to keep those boots from actually cracking. So that's kind of an anti-ice thing where it gets the ice off the airplane before. I thought there was a picture here, and I apologize for this. Yes, here it is. There is also kind of an anti-ice system. If you look here at 7.49, you can see the leading edge here of this wing, and you can see these little beads of this fluid here. So on the leading edge of these, what they refer to as a weeping wing system, is that this is a way to actually keep the ice from forming on these wings in the first place. And these systems have these laser-etched holes on the leading edge of the aircraft. It can be on the wing, it can be on the horizontal stabilizer, the vertical stabilizer, anything basically where that's going to be hitting that supercooled water droplets that would tend to freeze on that wing anyway. So the way these work, there are these reservoirs that you put this glycol-based system, this solution rather, in these tanks in the airplane. There's a pump, series of pumps, and normally you have a high and a low setting here for the pumps to move the fluid. The trick to all of this is that you have to activate these systems before you fly into an area of known icing. For instance, if I know that I'm going to fly into ice, then I need to activate that system, let that fluid flow from the leading edge to coat the wings and horizontal stabilizer, vertical stabilizer. So then the ice will not form. Now that is if that system is set up for what they call FIKI, F-I-K-I, flight into known icing. Your aircraft has to be certified as such to fly into areas of known icing. There are other systems that are going to be certified for inadvertent ice encounters. So if you fly into an area of icing inadvertently, but you didn't mean to, sometimes these systems can give you the opportunity to get out of that system without any kind of detrimental ice formation on that airplane. Passenger jets, big airplanes with jet engines, they actually can heat the leading edges of the wings, horizontal stabilizers, vertical stabilizers, other components that with the bypass air generated from all of the heat that's created in those jet engines. And they can pipe that heat to the leading edges of those aircraft to keep those aircraft from forming ice if they're flying into those icing conditions. Now, when they do that and they bleed off a certain portion of that air, that hot air that heats those leading edges, it also robs that airplane of a little performance. So you kind of have to think, okay, I've got to keep that in mind as I flip that switch to know that my performance may be degraded slightly. It's not a lot, but depending upon conditions, that is a consideration that a pilot's going to have before they activate those systems. The propeller also is something else here that is also needs to be considered when it comes to de-icing. When you look here, you can see this is what we call a prop anti-ice boot, or what we refer to as a hot prop. Even in my aircraft, I don't have the de-icing elements on the leading edges of my wing or my horizontal or vertical stabilizer. I don't have that. Does that mean I don't have a de-ice system? Actually, my propeller has what we refer to as a hot prop. So those lower elements here, where it's slower moving those are going to be the areas on a propeller that could be more susceptible to developing ice, where that slower movement closer to the hub here in this inboard section of this propeller. So there's a heater that actually can heat that element here to help keep that ice from forming. Now, it is a big amperage draw on my electrical system. So again, when I flip that switch, I need to know that everything on that airplane electronically is working properly before I flip that. And if I'm having other issues with that system, I also have to know that if I flip that switch, I've got to turn other things off in order for me to use it if the chips are down. Similar to the Weeping Wing system, there is also a system that actually sprays that de-ice fluid also. And so you have certain propellers that have the hub that sprays this fluid, and it'll spray it on the propeller. But the other thing that it does is that it sprays that fluid back. So now you actually get some of that fluid on the windscreen, which can help keep that windscreen from actually developing ice. Because otherwise, you basically have a defrosting airflow where you have warm air that gets blown up on the backside of the windscreen to help keep that ice off. Sometimes that's enough, sometimes it's not. Some aircraft have a certain glass plate that sits directly in front of the pilot. It's not very big. It's about the size of an iPad. And that glass plate is heated. That glass plate basically gives the pilot just a little bit of room so that if you're making an approach in icing conditions, it can actually keep that part out so that they can visually identify the runway when they're landing that aircraft. So there are some other anti and de-ice systems out there, but these are just kind of the basics. And with that, we sort of get here to the end of this chapter. Now, the one thing that I want to do is just kind of wrap this up here for you. Now, as we wrap Chapter 7 up, the big takeaway from this is the fact that there are a lot of other things working in that airplane beyond that propeller, that spinny thingy that we see out there in the front or the back of an airplane, in addition to that wing. There's a lot of things going on. So this again are one of the other challenges when you're learning how to fly an airplane is learning how all of these systems work, how to monitor them correctly, and probably more importantly, what to do when something goes wrong. Notice I didn't say if something goes wrong. Your mindset has to be that when something fails, I know what to do because I have prepared, I have trained, and I am mentally ready for it when it happens. That's kind of your mindset. So that ends Chapter 7 with our systems episode here. Hope you've enjoyed it. And also look forward to the quiz. Check in, make sure that you've looked at what other episodes that are coming up. I do want to tell you that with some of the other episodes, they are going to get to be a little bit more challenging for those of you that have been asking about that. So be careful what you wish for with those because we can make things challenging but fun. Okay? Guys, thanks for tuning in. I look forward to seeing you next time.